Hello students, welcome to EPG Pathshala. I am Dr. Dinesh Kalyansundaram from Indian Institute of Technology, Delhi. Today we are going to talk on a module, partial differential equation. The objective is first to understand what is partial differential equation, how it is different from ordinary differential equation, what are the characteristics. Then we will divide, classify them so that the different solution methods for different classifications can be applied. Finally, we'll end up with the application. What is PDEs, which is partial differential equation? How is it different? The very first phenomena is when any phenomena depends more than on one variable. Then it comes under partial differential equation. So we can say a representation of various physical and geometrical problems is the origin of partial differential equation, where a function or physical phenomena depends on more than one variable, that is two or more variables. For example, problems in fluid and solid mechanics, heat transfer problems, then electromagnetic theory, quantum mechanics, and all other physics problems, everything leads to partial differential equation. Why partial differential equation? Because when there are more than one independent variable on which everything is dependent on. For example, if temperature is dependent on x, y, z and z axis and also on time. Now there are four independent variables, and the temperature is going to vary with respect to where you are going to see the temperature. So it's going to vary with respect to x, y, z, and it's also going to see when you are going to see the temperature. That means it's going to change with respect to time t, right? So the moment you are going to write any equation where the temperature, which is the variable of interest or the quantity of interest you are wanting to see with respect to different or many or multiple independent variables like x, y, z and t. Why they are called independent variables? Because irrespective of what value y is, it's the y axis can never change what is in x axis, or what how x axis will behave, or how time is going to behave. So they are all independent axes or independent variables. So that is the reason why any variable or function we want to study is going to dependent on all these four completely independent variables. So at any point the maximum number of truly independent variables can only be four. Okay. And these problems will come in solid fluid mechanics, in electrical problems, in everything. So PDEs is the only way that we can represent and solve more complex phenomena, physical phenomena. We are going to see what is the partial differential equation definition. When we have two different independent variables, that means they are not a function of anything, they are just completely separate, and any function, let us say u or variable u, is going to change with respect to both of these two different variables. The two different variables can be x-axis, y-axis, or like what we are seeing, it can be x and t. That means x is one of the dimensions of space and time is dimension in time, and t is dimension in time. When we have any variable, even our movement is a variable, and we are dependent on both the space, we are going to change with respect to where we are walking, and we are going to change with respect to the time. So u is the dependent variable, and xt or xy and xyt z, these are all going to be independent variables. The moment we are going to deal with such a situation, then we have to definitely use partial differential equation and not ordinary differential equation. Now, how do we do partial differential equation or denote it? We denote it by a small dou as shown in the figure, right? So it is just the mirror image of writing d. It's dou u bracket x comma t. That means the u is a variable we are interested in, but u unfortunately or fortunately depends on the two independent variables x and t. So it means the function, it's a function of x and t, and then we are going to differentiate with respect to t. But it does not mean, since we are differentiating with respect to t, we cannot say it is only its ordinary differential equation. So the right hand side is again c times dou u of x comma t by dou x. So the whole equation, there is a relationship between u and t we want to are interested in, and u and x. So these kind of situations are captured better by partial differential equation. We are going to see notations. Notations meaning short forms. So u of t is actually the same as dou u by dou t, and u of x similarly. Then u double t is going to be dou squared by dou t squared times u, and dou xt is going to be dou x and dou t. And whether you do dou x or dou t, it doesn't matter. The order doesn't matter. And you can do it for xy, you can do yt and xx. So as shown, you can use them later. We are going to see what is the need for partial differential equation. Example 1 is we want to understand the heat distribution in a body which is actually different sizes. Okay, let us see. The first size, let us see, you want to have a thin wire, very thin wire. So the thickness is nearly very small compared to the length. So we want to see the heat conduction in this wire. If you see the heat conduction in this wire, go to the bottom left corner. So you can just write the differential equation. Dou u by dou t is equal to c squared, dou squared u by dou x squared. We are not going to see how the differential equations are derived here, but we are only going to see how the partial differential equations have to be understood and operated upon. Then let us say we have a plate and you're heating a tawa or whatever it is. So then there is the heat spreading all over in x and y. So that time the differential equation is given in the middle of the page, which is dou u by dou t is c squared dou squared u by dou x squared plus dou squared u by dou y squared. Then let us assume it is a complicated structure as shown in the right side image, three-dimensional heat flow. So that time there is another factor going to get added in terms of space, dou squared u by dou z squared. If you go to the very first equation, dou u by dou t is equal to c squared dou squared u by dou x squared. Since there are only one dimension, we are only writing dou x. Since in the second one we are having two dimensions, we are having dou x and dou y. In the third we are having with respect to three dimensions. In many cases we will try to not to use the third dimension. It's actually easier if we reduce the number of dimensions by making approximations throughout the program, or throughout the problem solving method. We're going to see another example where you have a tightly bound string and you want to excite them. So here the solution is going to be dou squared y is the displacement, and that y displacement can be a function of both time and the function of both space, where at what point it is. So it is function of both x and t. So we are writing dou squared y by dou t squared is equal to c squared dou squared y by dou x squared. We want to find the order of the partial differential equation. Again, order of the partial differential equation is equal to order of the highest order derivative. That means the bottom one, dou x squared or dou y squared or dou x cube, that is going to be. And so the order is defined in ut, which is then it's going to be first order. Second order will be ut is equal to uxx. Now the uxx is the second order, so we will have to write it as second order. But if you see ut, it is going to be only one order, but it is not the highest derivative. Third order is going to be similarly u xxx, that means it is getting dou x cube in the bottom, that's why it is in third order. And fourth power will become when it is differentiated 4 times. We are going to see the difference between linear and non-linear partial differential equation. As we saw in ordinary differential equation, if two derivatives don't get multiplied, then it's going to be a linear term. If two derivatives, let's shown in the bottom 3 equation with an underline, dou u xt is getting squared, so it's getting multiplied twice. Or there is the second where there is a root, the power is 1 by 2. Or in the last equation where u of xt is multiplied with u of t. So these are non-linear differential equations. We are going to see constant versus variable coefficient of partial differential equation. What is a constant coefficient? When the numbers are constants or integers. When it is variable, when the constant, let's say like here in the second equation, second term, it is e power minus t into u of xx. U of xx is the differential equation term, and e power minus t is the coefficient. Coefficient is changes with respect to time, so it is a variable coefficient. We are going to see what is a homogeneous versus a non-homogeneous partial differential equation. A homogeneous equation is when all the terms are there and it is equated to a zero term. Zero term meaning it is not having any function u. For example, here it is u tt minus 3 u of x, u xy is equal to 0. In the second term, second equation, we can see u of tt minus u xx is equal to x squared into sin t. So in the first one, we don't have any functions left which is undifferentiated form of x or t. But in the second, we are having undifferentiated x squared and sin t left behind. So the first one, when such terms are not there, is called homogeneous, and when such non-differentiated terms are left over, then it's non-homogeneous. We want to understand the types of differential equations, partial differential equations. Now cut the equation a times uxx plus b times uxy plus c times uyy plus d is equal to 0. Now if the solution, the b squared minus 4ac, that is where we find the roots of the solution. If that b squared minus 4ac is that less than 0, then it's going to have an elliptical profile. So if you plot those solutions in a graph, it will look, all the values will lie in an elliptical form. It is a closed form solution. B squared minus 4ac, if it is equal to 0, then it will be parabolic. Parabolic meaning one end is closed, the other end is open. Hyperbolic. Hyperbolic, b squared minus 4ac is greater than 0. So that means to a certain part closed and certain part it's open, but it is open on both ends, but it's not valid in some center area. We are going to see a Laplace equation, which is a elliptical partial differential equation. Dou squared of u of xy by dx squared and dou x squared plus dou squared u by dou y squared is equal to 0. Now we can see a is equal to 1, b is equal to 0, c is equal to 1. So b squared minus 4ac is less than 0. So the the equation is elliptic. So one possible solution is u is equal to e power x times sin y. So u of x is e power x sin y, u xx is e power x into sin y. Then if you add them, then it's going to become 0. We are going to see example of parabolic partial differential equation and hyperbolic differential equation. Parabolic heat equation is the best parabolic equation. Here you can see the A is equal to alpha, B is equal to 0, C is equal to 0. So B squared minus 4AC is 0. Then the heat equation is parabolic. In hyperbolic, the ideal case is a wave equation, which means the wave traveling in a string or wave traveling on the surface of water. Then it becomes A is C squared, which is definitely greater than 0. B is equal to 0, capital C is equal to minus 1. So the wave equation is hyperbolic. We are going to see how to represent the solutions of a partial differential equation. The first left side graph shows how the temperature curve changes with respect to time, and you can see it is a function of time, it is changing. In a two-dimensional graph, you can mention the different points time t with respect to x and y, and the height will give the temperature, and the position in the graph is going to define the time with respect to x or x with respect to time. The third way you can do is you can see how the heat profile for a particular temperature is actually flowing. So let us say these are temperatures of maybe 100-degree curves, and then you can say at time t is equal to 3.5, the inner curve, the heat was actually only in the inner curve, and at time t is equal to 5.2, it became a bigger curve. So there are different modes of representation of the results. We are going to see how for a small rod the temperature can be represented when it is getting cold. We have put a rod in ice, and we are going to see how the temperature is going to vary. The differential equation is going to be dou squared t divided by dou x squared minus dou t by dou t is equal to 0. Then we know at the time t is equal to 0, there was a temperature. So t as a function of 0, that means at x is equal to 0 and time t is equal to t, it is going to be t of 1 comma t. So that means at point 1, which is the extreme point, and time t, it is equal to 0. Then t of x is equal to x comma 0 is equal to sine pi x. So if you plot as a graph, you can see the temperature at x time is higher, then time t is equal to 0 is higher, and slowly it starts decreasing. So you can see a smaller curve. At time higher, which is h, let us say, than 0, the temperature starts dropping. That's what we are seeing. Existence and uniqueness of solution of PDE. What is existence? Existence is we should first find out whether a solution for any problem or a given PDE, does it exist or not. That means whether the solution that you are saying, is it truly valid or not. So you cannot say time is equal to minus 50. When the time is always given in positive quantity, then it cannot have a value or a solution where time is given as minus 50. So that is existence. Then the second thing is uniqueness. Whether the solution is the only solution for the problem. Because as we saw earlier, also in ordinary differential equation, there can be more than one solution to a problem. So we should always think that given a differential equation, we have to see for multiple solutions. Okay, so we should always double check if there is only one solution. We have to find out whether it's a only uniqueness solution or not. Then PDE involving time, that means solutions for time variable greater than 0 are only up to a given value of time. That we have to also make sure. One also want to know whether the solution of the problem depends continuously on the described data. We are going to see the boundary conditions for PDEs, and this is the same as for ODEs also. So you can see the figure, and let's say the temperature T is going to be dependent on time small t and x. So you can write u of 0 comma t is equal to 0. That means if the temperature on the boundary, left boundary, irrespective of time, if it is 0, then only you can write. And this can happen only in an insulated condition. So if your thing is not insulated, do not write u of 0 comma t is equal to 0. That means at all times it is no change in the temperature or u. Then 1 comma t is equal to 0. That means the temperature on number 1, which is the extent of the other boundary. 1 is x is equal to 1 or the extreme boundary. That is equal to 0, provided it is actually 0. If it is changing, then you will have to take those terms into account. Then u of x comma 0 is equal to sine pi x, which is the bottom line. That means you are telling what is the initial function at time t is equal to 0. However, be careful that the boundary conditions are perfectly set. See, when you say at time t is equal to 0 sine pi x, then this is called the initial condition. Some people may use the word initial condition. So at time t is equal to 0, if you mention at any point, okay, whether x is equal to 0 or x is equal to 1 or simply put x means it will take all the values of x. If that is equal to 0, then that is called the initial condition. Now if you talk about on x but with respect to time, for an extended period of time, the first two boundary conditions, x of u of 0 comma t and u of 1 comma t, those are called boundary conditions. In total, all three can be called boundary conditions, but if time t is equal to 0, then it's called initial condition. A solution to PDE is, generally speaking, any function of the independent variable that satisfies the partial differential equation. However, from this family of functions, one may be uniquely selected by imposing additional initial and boundary condition. Analytical solutions are possible for simple and special cases only. To make use of the nature of the equations, different methods are used to solve different classes of PDEs. Some methods to solve PDEs. This is very critical to understand. First thing that we can see is separation of variables. A PDE is an independent variable one, and where we can separate the equations on one side. For example, left hand side will be containing only one set of independent variable functions, and the other side will contain only another set of independent functions. When we have more than two independent variables, how do we do that? And that's what we are going to see later in the courses, how we can deal with x, y, z and stuff. Then, so separation of variables is applicable in two independent variables or more. Direct integration. Solution can be also found out by direct integration, that we can tell you when we are going deeper into the subject. Numerical methods. Numerical methods is the most used industrial type of procedure, because when it is really difficult, when we really have a very complicated problem, how do we do that? So we are going to start with, like, let's say we are going to assume a solution, and we are going to first put that, and we are going to see the difference in the error, and then we are going to slowly change the solution so that the error minimizes. Okay. Now this is completely very complicated, very difficult, or very at next level we should do that. So we are not going to do any type of numerical methods in this course, because this is a fundamental course. Separation of variables, and this is very important to understand that this form of solution is going to be significantly used when we are solving PDEs. It involves a breakup of the function into each of the variables, each of the axes. So for example, we want to solve u dou squared u by dou x squared minus 2 dou u by dou x plus dou u by dou y is equal to 0. We are going to assume the solution x, or sorry, u is a function of capital X and capital Y, which are in terms a function of small x and small y. So why do we do that? This is kind of similar, or the idea is a very complicated problem can be always written either as a product, like you see now, or as a sum, which you saw in the ordinary differential equations, and the solution. So this is called decoupling of the problem. Okay, so we are going to separate the variables. So now if you substitute in the equation earlier dou squared u, if u is equal to capital X into capital Y, then dou squared small u is going to be capital double dash x and into y, then 2 times x dash, capital X dash into y, then x into y, capital Y dash is equal to 0. Now, what is separation of variable mean? That means we are going to separate these two equations completely, one side x and one side y. So we are going to do that like it is shown here. Then we can solve them more easily. This is called separation of variables. It is continued in the next slide. Separation of variables. What we can do is, once we separated the two equations, we can say that this ratio is equal to k. K can be any number. K can be 0, 2, but it cannot be a function of anything else. It's just a proportionality constant. Now, if you solve for x and y, you can easily find out that capital X is c1 times e power 1 root of 1 plus k times x, then c2 times the same exponential constant with just the change of plus to minus. Then y, similarly, you can find out is c3 times, which is a constant, times e power minus ay. The whole solution is just going to be the product of these two functions, u times x, u is equal to x times y. That's what we have written. Direct integration method. The simplest form of partial differential equation solution is that when we can directly integrate. Now assume the problem u f x x x is equal to 12x squared t plus 1. Given the solution, boundary conditions are x is equal to 0, at x is equal to 0, u is equal to cos 2t, and u of x is equal to sin t. U of x meaning u is dou u by dou x. Now we can integrate it directly on both sides, because we are not integrating with respect to t, but because we are integrating with respect to x. Now when you integrate, the first step, u of ux will be equal to 12 t plus 1 into x cubed by 3 plus psi of t. Now we should write it as a constant, but why are we writing as psi of time? The psi of time is written because we are integrating with respect to x. So any function which is a function of time will be considered as a constant. But if you see the boundary condition, we are having terms of time t. So that is why we have written the constant, which is a constant when it is viewed because from x direction, but it is still a function of time. So when you equate it psi of t with respect to the boundary condition x is equal to 0, you can find out that psi of t is nothing but sin t. Because at x is equal to 0, u of x will become the whole term 12 into t plus 1 into x cube is going to become 0. So u of x is equal to become sin t. Then we integrate one more time to find u, or the function value u. Once we integrate, similarly as shown in the figure, we can see the solution in the next slide. We have, after integration, we have u is equal to x power 4 t plus 1 plus x sin t plus cos 2t. Again we are using the function psi of t or psi 2 of t and equating to the boundary condition. Then we will find out the solution is cos times 2t, which is a constant value. The whole equation is as shown. Applications of PDEs. PDEs are used to model many systems in many different fields of engineering and science, especially the second order PDEs. Second linear order PDEs are most important set of equations, and most physics problems are dealing with that. Each category relates to specific engineering problems. Different approaches are used to solve these categories, and that's what we will see later. Important examples are heat equation then Laplace equation and wave equation. We are going to see the solution of the heat equation. Here we are going to denote U as for the temperature, because time T is going to get reserved for, capital T is going to reserve for time. So the general equation is dou U by dou T is equal to alpha times dou squared U by dou X squared, dou squared U by dou Y squared plus dou squared U by dou Z squared. Now in one dimensional, the Y and Z terms will be removed, and the alpha is going to be thermal diffusivity. For general case, you can just assume as 1, but it is not 1. It's going to be different in different cases. We are going to write U as a function of capital X, capital T. Then we can separate as shown in equation 3, x double dash by x is equal to 1 over alpha, t dash by t. Then you can solve two equations separately, assuming it is equivalent to a constant small k. Then it leads to ordinary differential equation. Then you can solve it, and you can see the solution in the next slide. And when we solve the equations 4 and 5 as shown in the figure, can get different equations depending on what is the value of the constant. We can assume the value of the constant in case A equal to p squared and is positive, then you get the solution x is equal to c1 times e power px plus c2 times e power minus px, and t is equal to c3 into e power c squared p squared t. The solution is going to be x into t. When it is negative and minus p squared is going to be different as shown here, and when k is equal to 0, then we have a different equation. We are going to see the solution of the heat equations for the various conditions of constant k or p squared given in the previous slides. We can have different solutions, and it is going to be dependent on the boundary conditions. Laplace equation. Laplace equation dou squared u by dou x squared plus dou squared u by dou y squared plus dou squared u by dou z squared is equal to 0. This is used to describe steady state distribution of heat in a body. Also, it is used to describe steady state electrical charge in a body. We are going to see the solution of Laplace equation. As you rightly guessed, since we have three different independent variables, we can write the solution for u in terms of x, y, capital Y and capital Z. Then if you differentiate and substitute the u in the equation 1, then you will end up getting 1 over x dou squared of d squared of capital X plus divided by d squared x, and then 1 over y. Similarly for y and z is equal to 0. The way we can assume a simple solution is the first term we can assume it is equal to k squared, the second term we can assume it's going to be equal to L squared, the third term we can assume it equal to minus of k squared plus L squared, then the sum is going to become equal to 0, right? So k squared plus L squared minus k squared minus L squared is equal to 0. So then if you take individual values and equate it to k squared, L squared, Z squared, then you will find the last equation. Continuing the equation of solution of Laplace equation, then we can solve these three equations as shown in the top page. Then we can solve them as one-dimensional ordinary differential equation. We'll get x, solution for x, y and z as shown. The total solution is going to be just a product of all the solutions as shown. We are going to see wave equation. The only difference between wave equation and heat equation is, in the heat equation, it is only dou u by dou t on the left hand side. In the wave equation, it is dou squared u by dou t squared. Otherwise, it is going to be the same, and we are going to see the solutions in the next slide. We can just follow the same procedures which we have done before, and we are going to do step by step and come down to equation 4 and 5. So once we put for different cases of k, positive and negative and 0, we are going to have the following solutions for u. The final slide for the solution gives just the product of x and t as seen in the previous one, and this is the final solution for u for different cases of p. So students, let us now summarize what we have learned in this module. PDEs are very useful techniques to solve problems. Okay, and also remember, I have only talked about how to solve the PDEs. we have not discussed about how to derive a PDE for a given physics problems, because that is not the scope of this subject. If you want, you can go and refer any of the references, book references that I have given to you. Here we are focused mainly on the PDEs, how to solve the PDEs. The second important thing that you should remember out of this module is there are PDEs arise only when there are independent, more than one independent variable that your phenomena is dependent on or function is dependent on. In terms of space, there are only three distinct PDEs, distinct variables. One is x is y, and z axis, that is for space, and for time there is only t. So there for any common problem, there are only going to be four independent variables, and there can be many physics problems, and most of the physics problems or commonly used physics problems which uses PDEs are heat equation, then we have Laplace equation, and we have wave equation. And what do we learn from this equation? They are all ways in terms of linear second order differential equations. Okay, we have seen some analytical methods like separation of variables and direct derivative functions, how to solve the PDEs. So most of the simpler PDEs they can solve, or you can solve using these two methods. In real life complicated problems, let's say pipe water flowing in a dam or in a flood situation, okay, then complex PDEs are used, and we cannot solve them with just the analytical methods. Then we go for numerical methods. Numerical methods we have not dealt in this course, and that is a huge topic by itself. And so for basic understanding, I think you have to learn through different examples. And please remember, the key thing is to whenever there is a slide with only the equations, you can probably pause the slides and go through step by step until you practice the differential equations. You may not really understand the mathematics. So please pause any of the equation slides or solve problems that we have solved, and please work it out. Then it will become more useful for both of us. Yeah, thank you. Thank you.